Okay, so this is the review of what we did in the last class. We try to quantize the LC tank, right? So for an LC tank, we know that from our classical electronics, we know that it has a resonance frequency, omega R equal to square root L divided by C. It also has a characteristic impedance equal to, oh, sorry, this is wrong. Say it wrong. The resonance frequency should be square root 1 over LC, and the characteristic frequency is L divided by C. Okay. Now, so this is a very instructive example of very useful because we quantize the simple harmonic oscillator, and we find that we can use the similar strategy for the LC tank. If we recognize that its general coordinate, right, or maybe I just call it Q, right, its general coordinate is just the flux through the inductor, and then its generalized generalized velocity, sorry, q dot is just equals to the charge of this circuit. So in the classical framework, we know the Hamiltonian is q squared divided by 2c and flux squared divided by 2l, right? Flux, of course, talking about the flux going through this inductor, right? You have the flux, it's B field, and then the flux, of course, equal to the B times A, right? Times the area, the total magnetic field and total effective area. If you have many terms, you have N, you times N, right? So this is the Hamiltonian. So we agree with that, and I prove to you why it is, or you learn in other classes, right? Electromagnetic wave class, you know the energy on the capacitor is this, the energy in the inductor is this. We do some transformation by eliminating L because we know omega R equal to 1 over square root LC. So I can have 1 over L as C times omega R squared. So this is like what we did in the simple harmonic oscillator. And it resembles what? It resembles what we saw in the simple harmonic oscillator X, should be P, should be resemble the, I think I said something wrong again. I'm sorry. Not the velocity, right? It should be the generalized momentum is mapped to the Q. So this resemble P squared divided by 2m plus m omega naught squared divided by 2 times x squared, right? So you see that if we do the mapping by using also M to C, right? The mass in the simple harmonic oscillator mapped to the capacitor, then they are exactly the same, right? So because of that, we just do the same thing like we did in simple harmonic oscillator. We promote the Q and phi to Q and phi head, right, as an operator. And of course, just like the what we have the in simple harmonic oscillator, X hat, P hat equals to I H bar, right? Because now P is Q and X, which is Q, right? This small Q, right? This is X, right? Yeah, location coordinates, right? So this small Q is the flux, right? Is phi. So that's why we have phi and Q commutated equals to IH bar, right? So everything is the same. So naturally, I can write down the same equation for the lowering operator and raising operator, or we call it annihilation operator and creation operator. And they will obey this commutation relationship, right? And similarly, I can rewrite this as a combination of, I can rewrite the flux, right? The phi and the Q, right? Phi is the generalized coordinate and flux, the Q is the generalized momentum as a combination, linear combination of A and A dagger. And particularly, I can group this as something called phi ZFP, 0-point fluctuation. If you try to measure the uncertainty of the location or the flux or the momentum, which is the Q, you will get something related to this, right? So last time I did not prove this, but this is not difficult. I just quickly show you how to do it, right? The 0-point fluctuation equals to square root h bar divided by 2c omega r, right? But what is omega r? Omega r equals to like what I put above, square root 1 over LC, right? So with this, then 1 over L square root goes to the top, right? And then C divided by square root C becomes square root C, right? And what is square root L over C? It is just equal to Z, right? The characteristic impedance. And that's why phi 0-point fluctuation equals to this. So nothing special, right? And from there, then we also can create a number operator, which I did not write here. It is just equal to A dagger A, right? Just like what we did in the simple harmonic oscillator. Of course, A dagger A still have the A dagger. So sorry, this is typo. Should be head, right? Of course, A still has the A and A dagger still have the function of A dagger operates on N, give me N plus 1 times N plus 1. Right, give me a higher state, and then A operates on N, it gives me, I keep saying the wrong thing, right? This should be square root. I hope that you caught my mistake when I wrote it. Yeah, and this is square root N of N minus 1, right? So it still have the same function. And again, it has the Hamiltonian in this form. And this N is the eigenstate of the number operator. It's also the eigenstate of the Hamiltonian. And then the energy, right, is depends on the number of photons inside this circuit. Everything is the same as before, right? So think about this, because this is quite useful, at least for myself, to convince myself about what happened to the second quantization, right? So think about that. Okay, good. So then